Thank you. Thank you very much, Susan. And thank you very much, Katherine, for joining us at this odd hour. It's 6 a.m. in Melbourne, where Katherine is. And apparently her two children have served as a wake-up alarm this morning, and I made sure she's here with us. So it's a pleasure to introduce a speaker who's going to be talking about something that is of great interest to many people in the audience in the core where we are all based. When I reached out earlier in the year asking for topics that people wanted to hear about, multiple imputation was one of the commonly mentioned topics. So I was very happy when Katherine agreed to make this presentation because she's got a lot of experience in this area. She's a professor of biostatistics at the Murdoch Children's Research Institute in the University of Melbourne. And she's also the co-director of the Clinical Epidemiology and Biostatistics unit within the within this research institute. She's got extensive experience both in the planning of randomized and analysis of randomized control trials and observation studies. And she has contributed and she's led a framework, the development of a framework that lays out how multiple imputation must be carried out in observational studies. So clearly, you've got a lot of experience behind you. And thank you very much for speaking to us today.
Thank you for the introduction, Nadini, and thank you for coming and listening. I will just say my children are at the moment still in bed, although they're awake, but if they do come running past, I have tried to keep my husband to keep them out, but there may be a surprise appearance at some point, but we'll hope not. So I'm going to talk to you today about multiple imputation. It's very much a kind of overview of what it is and about how we plan, how we're going to handle our missing data. I'm very happy to take questions at the end. So as Nadine says, I've been working in this field for about 14 years. I do a lot of applied research, but the research around multiple imputation has really come out of the applied research, and you'll see a little bit of that in the presentation. So just a quick overview. I'm going to talk a bit about missing data, but quite quickly I'm going to give you a motivating example, which I'm going to come back to throughout the talk. I'll then tell you kind of what a multiple imputation is and a bit about the assumptions it makes. And then I'm going to focus on, when we face with an analysis we want to do or a study we want to do, and we know it's going to have missing data, how we go about that process of planning and then conducting and then reporting the analyses in the context of having incomplete data. And I'll just end with some very brief concluding remarks. So we'll jump straight in. So missing data arise in almost all research studies, and they arise for a whole different variety of reasons. So we talk about item missingness, by which we mean if we're collecting a whole load of things, a whole load of different questionnaires, we just have the odd thing missing. So you might have missed a questionnaire, you may have missed a question within a questionnaire, or you might not want to answer a particular question. So that's item missingness. You may also just decide you didn't want to complete that questionnaire, or it might be, I work a lot in children, so it might be a parent report. Once the parents didn't fill that one out because they weren't there or that day, or they didn't like the questionnaire. So you might have a whole questionnaire missing. We also talk about wave missingness. So quite a few of the studies I'm involved with are longitudinal studies. So these children are recruited and then they're followed up over multiple waves of data collection. And it may be that some participants just don't come to a particular wave, and they may or may not come back to future waves. They may be lost to follow up, or they may come back. The general rule is we like to try and minimize our missing data. Think about ways we can encourage those people to come back, try and get as many back for each follow-up as we can, try and make it easy not to miss questions. We might send out reminders if we're doing postal surveys, or but all what we should try and think about how we're going to minimize our missing data when we're setting out doing our study. But inevitably, we're still going to have missing data for whatever reason. So as I mentioned, this is a really big problem in all epidemiology, public health, clinical research, but it's particularly important in longitudinal studies because obviously you've got those multiple waves of follow-up, so you've got more chances for people to have missing data or to not come back. So it tends to be quite a big problem in that context. Now, when we think about missing data, that causes problems for our analysis. Most methods of analysis we want to do assume that data are complete and they're used to fit on complete data. So our standard regression models, they use complete data. And the typical way of handling the missing data is to just restrict the analysis to those who've got complete data on the variables we need for analysis. And that's called a complete case analysis. And that's still reasonably common today, but it also, it's always traditionally been the way we handle our missing data. So there are two major consequences of having missing data. The first one is it can introduce bias into our analyses. So this is particularly the case if the people with complete data are different to those with incomplete data, or we might talk about responders being different to non-responders. And what that means is that when we analyze our complete case analysis and we exclude those who don't have data, we've not got the same population we were trying to get at in the first place. We've got a subsample of that population. So we're not estimating the effect we want to estimate in the whole population, and that can introduce bias. The other major issue is that we can have a loss of power or a loss of precision. So if we, for example, had a sample size of 100 and 20 had missing data, didn't record their outcome, we'd suddenly only have 80. So we're not going to have as much information on the quantity we're interested in as we would have liked to have or as we plan to have. And this is particularly important if we're thinking about a standard regression and we want to adjust for a number of different covariates or confounders. If each of those confounders has a little bit of missing data, we might end up with a greatly reduced sample size when we try and adjust for quite a few of these different confounders. So it kind of propagates the problem. So this is the example I'm going to use throughout this talk. The Victorian infant cohort study. It's a cohort study that was conducted or is still being conducted in Melbourne. It's a longitudinal study of premature infants who are born across Victoria, and it followed them up throughout their childhood. And like I said, they're still going with longer term follow-ups now. So this study, they recruited all 298 survivors who were born either extremely preterm or extremely low birth weight in Victoria in 1991 and 92. And they also got data on 262 normal birth weight controls who were roughly matched for age, gender, and socioeconomic status. They were recruited at the time they were born, and they had quite a lot of data collected at that point about the pregnancy and the birth and any complications that they had during birth or soon after birth. And then they had major follow-ups at ages 2, 5, 8, and 18. I think they're just, I can't remember how old, where they're up to now, but they're definitely, they must be 30 now. So they're presumably on their next follow-up. So that table at the bottom just shows you the retention. So this, I'm just talking about that wave missingness. So, there was obviously 100% recruited, and then the 2-year follow-up was pretty good. And as you can see, as the time goes on, that follow-up rate drops. And by 18, the follow-up rate is only around sort of 55–60%. So we've lost a good 40% of our participants. And this is fairly standard in terms of a longitudinal study at the kind of follow-up rates you might expect to see. So the example I'm going to use through this talk is one that was published on this cohort. And basically, there's more and more of these extremely preterm, extremely low birth weight children surviving into young adulthood. I'm just going to say, I'm going to start calling them preterm children because it's a bit of a mouthful talking about extremely preterm, extremely low birth weight. So when I talk about preterm, that's what I mean in this context. So preterm survivors are at increased risk of lots of different problems as they're growing up, in terms of physical problems, cognitive problems, and psychological problems. So obviously, a lot of them have a lot of issues to deal with, particularly compared to their normal birth weight counterparts. So the aim of the question I want to answer here is to compare the preterm children's self-reported quality of life when they're adolescents, so at that 18-year follow-up, with that of normal birth weight controls. The paper that was originally written on this question was just a descriptive question, just describing the quality of life between the two groups. I'm going to, just because I need it for what I want to talk about later on, I'm just going to assume I actually want to make that's a causal question. So I want to know about preterm birth causing poorer quality of life later on. So I'm going to adjust for confounding, and that'll come up a little bit later. It just lets me illustrate a few things a little bit better. So if I do, sorry, did someone speak? Okay.
I think that may have been in your background.
Oh, maybe, I don't know. Okay. So if I address this question, if I did my complete case analysis, I'd be excluding over 40% of study participants. So that's I have a problem with missing data here, and I need to think about how to deal with it. So when we think about how we want to handle our missing data in the analysis, whatever analysis we do, we have to make some assumption about the missingness mechanism, so why the data are missing in the first place. So there was a seminal paper by Rubin back in 1987, and he laid out 3 different assumptions you can make regarding your missingness. So firstly, you can assume the data are missing completely at random, and that means that the probability of the data being missing doesn't depend on any observed or unobserved data. It's just completely random. So if you had your pile of questionnaires and you'd taken them home to enter into the computer and the wind blew some away, they'd be missing completely at random because it's nothing to do with any of the data that's being collected or not being collected. It was just a completely random sample. So that's one assumption we can make. Another assumption is we could assume the data were missing at random. And that means that the probability of data being missing doesn't depend on unknown values. It only depends on the observed values. So conditional on the data we have about the participants, the probability of missing is completely random. So in this case, if males were more likely to have missing data than females, but we knew who was a female and who was a male, and there was no other reason behind the missing data, that would be missing at random. So there can be predictors of missingness, there can be variables which predict missingness, but they're known and you have data on them and you can adjust for them. So that's the assumption the data are missing at random. Missing not at random means just the opposite of missing at random. So it means that whether data are missing or not depends on values of known and unknown data. So you can never quite predict the missingness because you've got some data that are unknown there. So people often use these 3 assumptions to guide how they're handling missing data. More recently, we're starting to move to causal diagrams, otherwise known as directed acyclic graphs, to outline our missing data assumptions. I'm going to show you an example and talk a bit about what they are later. So I'm just going to park that for now, but I will come back to that. So when we think about our standard complete case analysis, so excluding those who have any missing data, that's generally only valid if the data are missing completely at random. And there are other situations where it is valid, even if that's not true, but I'm not really going to go into that too much because it gets, this gets quite complicated. But basically the complete case analysis makes a very strong and pretty unrealistic assumption about your missing data. And if that assumption is wrong, that's particularly when you can introduce bias into analysis. So if complete case analysis isn't going to be great, then what else can we do about our missing data? So there's a number of kind of simple ways we can handle our missing data. So I've given a couple of examples there. If we have missing outcome data, we could assume those with missing data have a good or a bad outcome. So in our preterm example, we could assume the quality of life in those who have missing data is pretty low, and we could set some kind of value to that. The trouble is that's a very, very strong assumption again. And when we do an analysis, so if I assume my quality of life is 0.5 for those who've got missing data, for example, I then assume that that 0.5 is known in my analysis, which is not true because I'm guessing what it is. So I'm not incorporating the uncertainty that I didn't know what that value was. Something a little bit better we could do is we could assume the missing value were either the average of the observed values, or we could use some kind of regression model based on the observed data to predict what the missing value was. So the problem with that, I mean, again, when you do your analysis, it assumes that that value is known. It's not allowing for the fact you didn't know that value, that you were using some kind of model or some kind of average to estimate what that value is. So multiple imputation is a more principled approach because it allows for this variability, the uncertainty in the values that we're guessing, and it makes much weaker and more realistic assumptions about the missing data than, for example, the complete case analysis, because it's valid if the data are missing at random. So it's that weaker assumption. So I'm just going to spend a bit of time now talking you through multiple imputation. It's a two-stage approach. What we do in the first stage is we create some M more than 2 imputed data sets. So in each of those data sets, we fill in those missing values using some kind of regression, normally a regression model based on the observed data. And then we take each of those data sets and we analyze them using our standard methods, which assume we have complete data, and then we combine the results. And this is most easily explained in a figure. So on the left, this is our data set. So each row is a different participant and each column is a variable. And you can see there that the second participant has the first variable missing and the third participant has the second variable missing. So those holes in the data set are the missing values. So what we do is we copy that data set M times, and in each of those data sets, we fill in those missing values using some kind of statistical model. And we'll talk a little bit about the model because setting up that imputation model is really the key step of this process. So those filled in values, as you can see there by the different colors, they're different across each data set because the model predicts them slightly differently. So it's allowing for this uncertainty that we didn't know what those values were. We then use our standard analysis, which might be a regression. We do come back to it, but in our case, the quality of life is very highly skewed. So we actually use median or quantile regression. So here we would fit our quantile regression in each of those data sets to the full completed data set with those filled in missing values. And we estimate our parameter of interest, which in my case would be the difference in quality of life between the preterm group and the term group on a median scale. So we estimate that quantity in each of those M data sets, and then we combine those results to give us an overall estimate. And we combine the estimates and we also combine the variability. And I'm going to show you some formula for that, which you may or may not follow, and that's fine, but it's just to know that you're allowing for the fact that those values are different across the different data sets. So just to go into it a little bit more, I'm not going to go into it any more than this, and if you don't follow this slide, don't worry too much. But the actual principle of the method is that we draw those imputed values from the predictive distribution of the missing data given the observed data. And this, you've probably heard of Bayesian statistics, so this is actually a Bayesian approach. What this actually means, if we have missing data in just one variable, so in this example, we've got our data consists of a y, an outcome, and 2 predictors, x1 and x2. And if we just have x1 incomplete, what we do is we impute the values for x2 using, if we assume they're all continuous, using a linear regression of x2 on y and x1. So that's just that equation there. And we've got just the error term there, which is a normally distributed error term. So that's just a standard linear regression model. We fit that model to the complete cases, and we get an estimate of those betas and the S, the error term, the standard deviation of the error term. And then what we do is we use that model to draw some values for what X is from this. This is predicting X. And then we put those new values of X that we've drawn back into the equation and re-estimate beta and S. And we just keep doing that. So we keep getting new observations, new draws from this model for X2, and then we re-estimate the parameters of the model. And we keep doing that, and each one of those becomes one of our imputed data sets. So I hope that makes sense. You don't need to be able to follow this very, very well. When you do this in a statistical package, it gives you the answer. It does this all behind the scenes. What you often find is you've got missingness in more than one variable. So especially if you're having, things you want to put in the model to predict the missingness, they've often got a little bit of missing data themselves. So as soon as you have missingness in more than one variable, you need to think how you do that. So it's not, you can't just use, you can just use standard linear regression, but there's two general ways of doing it. The first thing you can do is each of those incomplete variables, you can assume has a multivariate normal distribution, and you draw all those values from one big joint multivariate normal distribution. So the appeal of this approach is that it's got a strong theoretical basis, and it's quite simple to specify because you just specify the 10 variables of missing data and it fits this big multivariate normal distribution. The disadvantages with it are if you have a mixture of binary and categorical variables and some continuous variables, then it all imputes it from this multivariate normal distribution. So the values you get back, the imputed values you get back, aren't going to be a 1, 0 if it's a binary variable. They're going to be on a continuous scale. So you might have values of 0.5 or 0.4 or whatever. So if you do that, then you need for some analyses, if that was your outcome and you're imputing a binary variable, you might have to round it for analysis because you wouldn't be able to fit your logistic regression if you had values which weren't 0 and 1. So sometimes you may need to round variables, then it's a bit unclear how best to round them because different rounding methods can introduce bias themselves. The other disadvantage is if you have some kind of interaction or non-linearity in your relationships, they're not easily incorporated using this multivariate normal approach because it fits this single multivariate normal imputation. So it does have disadvantages, but it's generally been shown to work well, even if you do have binary and categorical variables. The not being able to incorporate interactions in non-linear terms is more problematic, but we don't always want to include those anyway. So it does have quite a lot of use. The other way you can do it is called either fully conditional specification or it might be chained equations. Some people call it MICE, multiple imputation via chained equations. And what this approach does is it fits a separate univariate regression model for each incomplete variable, and then it cycles through them. So it imputes the first variable, one variable first, and it imputes the next one, then the one after, using the imputed values of all the other variables, and then it cycles back from the top. So this is very, very flexible because you can tailor each univariate imputation model to the variable type. So you can use linear regression if you have a continuous variable, but you can use logistic regression if you have a binary variable, which means that when you impute that binary variable, you get back a 0 or a 1. And you can use ordinal logistic regression for categorical variables. So it's got that very flexible approach, and it means you get back the variable type that you put into the model in the first place. You can also, because you fit univariate models, you can include different sets of predictors for each univariate model. You can incorporate nonlinear terms and interactions very easily. The disadvantage is it doesn't really have a theoretical justification, and because each regression model is set separately, you may not have it may not correspond to an actual joint distribution which makes any sense. And it can, if you've got large data sets, you have to set up each one of these regression models separately. So it's a bit more fiddly to do, but it has that major advantage if you get back the variable type you put in. So both approaches have shown to be very similar and both work very well. So it's not actually too big a decision, really. So you've done your imputation, you've chosen your imputation model, and we'll talk a little bit later about how you choose that. You then analyze each of the data sets separately using your standard method of analysis, which might be a linear or logistic regression. And then you combine the estimates across those M imputed data sets using what's known as Rubin's rules. So the overall point estimate is just the average of the separate estimates. And the variance is estimated by combining the within and the between imputation variance. So it allows for the fact that these, that the imputed values are different across different data sets. If you want the formula for those, they're here. So that's just showing you that the top line is just showing you that the overall estimate is just the average of all the M estimates. And then, yeah, the The within is just the average of all the variances, and the between looks at how far each estimate from each of those M data sets varies from the overall average data set. And then you add those two things together with a little adjustment. So again, you don't really need to follow this. When you do this in any statistical package, it does this combining for you. So the appeal of multiple imputation, well, it makes a weaker assumption about the missing data. It's valid if data are missing at random. It means you can include information from all those incomplete cases which you had to exclude for your complete case analysis. You can use most methods of analyses, because once you've got your completed data sets, you can just fit your standard method of analysis. The way it used to be used is you'd have one person do one big imputation, and then you'd have lots of analysts running different analyses on that imputed data. We're starting to move a little bit away from that now, and you'll see it in a little bit why. And the software available does all this stuff for you. So there's just simple commands that you can use. I don't know what programs you use there. We tend to use Stata. But there's simple commands in Stata and R and SAS that you can do this. So you don't have to worry about all the, the details that I've been talking about. And it's at the stage now where it's often requested by journal reviewers because it makes these weaker assumptions about the missing data. So these are quite old now. The first one's 2010, the second one's 2014. I did try and find a more recent one, but there hasn't been a review recently about how commonly it's used across sort of general journals. But you can see multiple imputation, back in 2010 was really kind of taking off there, and it really has taken off a lot more since then. But it does have a few downfalls. So people tend to think of multiple imputation as being a sort of simple approach. But actually there's, fitting that imputation model, there's a whole different way, there's 1,000,001 ways you could fit that imputation model, and they can lead to different results. But importantly, if you have a poor imputation model, it can actually introduce bias. So you do need to make sure the imputation model is sensible. It's not always clear that results are better than potential alternatives. As I did hint at earlier, there are situations where complete case analysis can be just as good and is a whole lot easier. And sometimes, particularly when I work with applied researchers, they think of trying to recover those missing values. And as I mentioned about, if you've got a binary variable, your imputation's not coming back with a 0 or a 1, it doesn't actually matter. You're not trying to recover those missing values themselves. You're just trying to make sure the inference, the big parameter estimate you get, is appropriate. So it's not about actually recovering those missing values because they're unknown. It's about making sure your inference is not biased. So that's a little whirlwind of multiple imputation. I'm now going to just talk a little bit about the actual process of doing this. And this is outlined in this paper we put together with an international group, a framework for the treatment and reporting of missing data in observational studies. And it goes through the process of first how, planning the analysis and thinking about setting up the imputation model. And then when you come to actually conduct the analysis, and then how to report the results from the analysis. So I'm going to run through each of those steps now. So there's a number of steps to planning the analysis. The first thing you need to do is actually identify the research question and plan the analysis you would have done if there were no missing data. So that's quite important. You think about what you want to do in terms of the parameter you want to estimate. And then the second step is, okay, I know what I want to do, but I've got missing data. How do I handle it? And then the next step is, well, if you decide you want to use multiple imputation, you need to think about how the multiple imputation is going to be conducted. What imputation model are you actually going to use? And there is a fourth step, which I'm not going to go into today, about thinking about whether you need to do a sensitivity analysis. And by that, I mean, think about whether data might be missing not at random. And if it is, conducting a missing not at random analysis. But that's a whole other talk. So that the first part of step one, identifying your substantive research question. So going back to my case study, I want to compare the self-reported quality of life between preterm adolescents and normal birth weight controls at age 18. And as I mentioned, I want to answer that as a causal question. So I'm going to use quantile regression. Quality of life is on a scale from 0 to 1. You can have values slightly less than 0 if you think your quality of life is worse than death. 1 is a good, I think I've got a great quality of life. So it's often very skewed towards 1. So we use quantile regression to allow for the fact it's very, very skewed. And I'm going to adjust for confounders. And in this case, my confounder is only really maternal education. So I've decided what my research question analysis is. I now think about how I'm going to handle my missing data. So when you're thinking about that and thinking about whether you should use multiple imputation, you need to think about really whether a complete case analysis is likely to be valid in the first place. And this will depend on how much information you're going to lose by doing a complete case analysis and what's the likely mechanism behind the missing data. So if I've got a lot of missing data, in my example, I've got over 40% of missing data. So I've got a potential to lose quite a lot of information. What are the likely mechanisms behind the missing data? I'm going to show you some tables to let you think about this. But basically, I want to think about, are there variables in my data set that predict the missing values? Because if there are, then my data is missing at random. So once you think about that, you then need to think about, well, would MI help? And MI would help. So we think about auxiliary variables. So auxiliary variables are variables that are not in your analysis, but they're variables that might provide information about what those missing values would have been. And again, we can look at our variables in our data set to help us to see whether there's variables that would help us predict our missing values. And we also need to think about which variables are likely to contain missing data. So I say are likely to there because sometimes, like in this case, we already have the data from the previous waves and we kind of know whether there's predictors of missing data, but that might not always be the case, particularly in a prospective study, like a trial or something. We've got to make some assumptions about what's going to be happening. And then we can use causal diagrams to help us think about some of these things, particularly that missingness mechanism. So a causal diagram just shows the relationship between different variables in terms of which ones we expect to cause which. So in our case, so I should say it's directed because so we have each variable's node, a circle, and we have arrows between the nodes. They've got an arrow head. So it's directed because we're talking about which variables cause which variables. And the acyclic part means you just can't go backwards because things in the future can't cause things in the past. So this is my little causal diagram for my example. So I've got my preterm birth there as my exposure. I want to estimate the relationship with quality of life. And my confound is maternal education. And so a confound is associated with both the exposure and also with the outcome. So that's my analysis. And if you want to read up on causal diagrams, there's a whole literature on that, but they're becoming more popular to explain, what assumptions we're making in our analysis. So in terms of missing data, I can add another node there for my missingness. So in this case, I've got missingness in my outcome at age 18. So I've now added that extra circle there. And I now put arrows, other variables that are going to, I think, are predictive of that missingness, whether data are missing in quality of life. So in this case, I think both preterm birth and maternal education are predictive of missingness, but I also could think about which other variables in my data set are predictors of missingness. And I have these previous measures of disability and previous measures of development that were collected at those previous waves of follow-up, which I suspect are related to missingness. And I've got a little dashed arrow there between quality of life itself and missingness in quality of life. And that's where the sensitivity analysis comes in. So if I believe that the quality of life is missing dependent on itself, I now have data that are missing not at random. So for the sake of this talk, I'm going to ignore that arrow, assuming that I've got the previous measures of quality of life as well, which might help with this. But you may want to think about whether the arrow's there, in which case you've got missing quality of life. Can you go to Debbie? Sorry, I did tell you they might pop up at some point. So if I want to think about whether variables in my data set are predictive of missingness, one thing I can do is look at whether there's differences in participant characteristics between those with incomplete and complete data. So this table shows I had a discussion with my clinical colleagues about which variables they thought might be predictive of missingness, and they came down to these ones. So that's ones we looked at. And rather than focusing on the whole table, if you just look at that row I've highlighted about disability, we can see there that in the preterm group, there's a much higher rate of disability in the incomplete cases, and the same in the normal birth weight controls. So there I can see that disability is related to missingness. So that's suggesting that there are variables in my data set which are predictive of missingness. And then useful auxiliary variables need to be correlated with the incomplete variables themselves. So a good way of looking at that is looking at the correlation between each of those variables and the missing and the quality of life at 18, which is what I want to impute. So looking down here, there's some correlations. They're not that high, but correlations of sort of 0.28, 0.29. So some of these variables are correlated with the missing quality of life, with quality of life, which means they would be useful in terms of trying to predict what that quality of life would have been. So these are quite useful auxiliary variables. So going back to my question, is a complete case, sometimes I call it complete records, but is complete case analysis likely to be valid? Well, no. Firstly, I'm excluding more than 40% of participants. And secondly, I know there's differences between my incomplete and incomplete data. So if I exclude them, I'm potentially getting biased results. Is MI likely to offer benefits? Well, there are some auxiliary variables here, particularly those previous measures of similar things at previous waves or experiences that these children have gone through at previous waves. And I've shown that they are associated with the incomplete quality of life variable. So yes, I do have auxiliary variables. So in this case, multiple imputation could potentially be useful. As I say, sometimes you won't know all this because you'll be doing this in advance, but you have to make some assumptions about these things. So I've decided in this case, I want to go ahead with multiple imputation because it's going to be beneficial. So I now need to think about how I'm going to conduct my multiple imputation. As I mentioned, this really is a key step in the process. So when you set up your imputation model, there's a whole number of decisions you have to make along the way. You need to think about which variables you're going to include and what form you're going to include these variables, the nature of the relationship, how you're going to impute, whether you're going to use fully conditional specification or multivariate normal imputation, how many imputations you're going to use, and what software you're going to use. So I'm going to run through some of these things just quickly now related to my example. But just the key thing when you're making some of these decisions, it's coming up more and more in our research into this method, is that you need to ensure that the imputation model is congenial with the analysis model. So I'm just going to have a quick interlude about what that means. So in order to ensure congeniality, you want to make sure that all variables in your analysis model are in your imputation model and are imputed in the same form as in your analysis model. So basically, your imputation model has to reflect your analysis model. And this comes back to when I mentioned earlier, it used to be kind of one person would do the imputation and lots of people would run their analyses. We're realizing that's not really the way to do it because the imputation model should be tailored to the analysis model. So just an example, if you're imputing non-normal data, even if that doesn't fit the assumptions of the imputation model, it's important to impute on that raw scale rather than doing some kind of transformation because you want to reflect the analysis model. And there's a method you can use called predictive mean matching. I'm not going to go into it too much, but it's rather than actually using a regression model to predict those missing values, you use a regression model and then you choose the case who's got the closest predicted value. So what that means is that you preserve any kind of distribution. So if you have a very highly skewed variable that you're imputing, the imputations will come back in the same highly skewed distribution. If I assume normality, my imputed value is going to be normal. So that's not going to be the case. So that is a useful method of doing that. The other thing is that any features in your analysis model need to be reflected in your imputation model. So if you have interactions or nonlinear terms in your analysis model, they should be reflected in your imputation model. Or if you've got a weighted analysis, or if you've got clustering in your analysis model, then you also need to incorporate that in your imputation model. So when you're thinking about setting up your imputation model, it's important to remember to make it congenial. So going back through that list of decisions, which variables should I include in my imputation model? Well, going back to congeniality, you need to include all variables in the analysis model. So in my case, I've got one outcome, one exposure, and one confounder. So those three variables have to be in the imputation model. You then also need to think about which auxiliary variables to include. And the most useful ones are those that are correlated with the incomplete variables. So in my case, you've often got sort of similar variables at previous waves, and they're good ones to start with. In my case, I discussed this with the clinical colleagues. The table I showed you before of all those different variables, they were all kind of somewhat correlated with the incomplete quality of life variable. So I included all those variables. So when you're selecting auxiliary variables, we generally have an inclusive strategy. The more variables, the better predictions we're going to get and the more accurate our imputation model is going to be. So we generally think of this inclusive strategy. So I ended up including 23 variables in my imputation model, and that's perfectly reasonable. Then what form of variables should I include? They should be in the same form as in the analysis model. So in my case, I just had main effects. I've just got one exposure and one confounder. So I just include those variables in the form they were in. As I mentioned, the nature of the relationship between the variables, I have no interactions, no non-linear terms, so I can just incorporate them straight into the model. The only thing to note here is when I looked at those correlations, I didn't actually show it on the slide, but the correlation between some of those auxiliary variables and the incomplete variables were different in the preterm and the term groups. And also there's some variables which are only relevant to the preterm group, some things that only the preterm group experience. So in my case, I actually imputed separately in the two groups because, like I said, there were some variables I didn't want to include in the normal birth weight group. How to impute multivariate normal or fully conditional specification. In the literature, fully conditional specification or chained equations is probably the most common. And I think it's because it comes back to you impute things on the same, or you get imputed values back on the same scale that you put them in. So you haven't got to make any decisions about rounding or anything, which makes things much easier. So that's what I did. So I used linear regression for my continuous variables. I used logistic regression for my binary variables and ordinal logistic regression for my ordinal variables. How many imputations? The general rule of thumb is that you need to have more imputations than the percentage missing data. So I had about 40% missing data in my outcome and not much in the other variables. So I had 40 imputations when I ran my models. And then which software to use? Multiple imputation can be conducted in most statistical packages. I use Stata, and there's commands mi-impute and mi-estimate, which I use to do this. Now, the important thing is that all of this should really be pre-specified, particularly for a prospective study. If you're planning on using multiple imputation, you should think about, well, why is that going to be the best approach? And if I'm going to do it, how should I do it? So this should all really be pre-specified in an analysis plan. And obviously that involves making some assumptions. So when you come to conduct the analysis, the first thing you do is examine the data, and you need to think about those assumptions you made when you were pre-planning and whether that's actually how it plays out in the data. And like I say, when you've got a study like mine where you've already got the data collected, you already know some of those things. So this step's perhaps less important, but you would have done those tables that I showed you before already anyway. But if you're doing this with a prospective study and you're planning it, you think about the assumptions you made and whether that's actually what happened. So here's some tables that can be useful to look at the features of the data. And we've seen some of these tables already. So you can think about the proportion of missing data in each of the variables that you want in your analysis. You can think about the table of observed characteristics for the complete and incomplete cases, which table you've seen before. And we can think about looking at which variables are predictors of missingness. So it's just doing that step 2, but a little bit more formally. And once we've checked the data, the next step is then to conduct the analysis as per the plan. And if you don't stick to the plan because you find the assumptions aren't valid, you may make amendments to the plan, but then you should acknowledge that you've changed the plan and why you've changed the plan. So here's just some examples of some tables you might think about. So we want to think about the proportion of missing data in each variable in the analysis. So there's my preterm is never missing. So I'm doing it by preterm in this case. And looking at what data was missing in maternal education. So it was about 10% in the preterm group, a little bit more in the normal birth weight group. And then how much missing data from my quality of life. And there's the reflected about 40% that we mentioned before. This was the table we saw before, looking at the summaries of the characteristics, the baseline, typically baseline or previous characteristics in the complete and incomplete cases. And then the final table, which, like I say, is a bit more of a formal assessment of the predictors of missingness. So in this table, I've done a logistic regression of being a complete case. So I've generated a variable, are you a complete case, yes or no, for the variables in my analysis model. And I've looked at these variables as predictors and using logistic regression. So these are odds ratios and p-values. So for example, there, we looked at disability earlier. So you can see there the odds ratio is 0.69. So you've got lower odds of missing data if you're disabled. So this helps you look at those predictors of missingness. This is about assessing whether your data are missing at random. So here there's clearly predictors of missing data. So my data are clearly not missing completely at random, they are missing at random. The next step is then to conduct the analysis as per the plan. Now in this plan, I knew there was lots of missing data. I knew some of the things that some of these variables were predictive of missing data. So I thought the data were missing at random. So I decided to use multiple imputation. So here my primary analysis will be multiple imputation. And I conducted a complete case analysis just to kind of back that up and see what difference it made. It's kind of a good sort of base case. So looking at these results, the group difference was pretty close to 0, slightly below 0, but pretty close to 0. And the confidence interval is reasonably narrow, around 0. So there's not really any evidence of a difference in quality of life between these two groups. And in terms of the missing data, you'll see here there's quite a similar estimate for the group difference between the two. There's not any, the conclusions are the same irrespective. There's not really any difference. You'll actually notice here the standard error is slightly larger from multiple imputation, the slightly wider confidence interval. That is seen a little bit. So the fact that the values were unknown is actually bringing in more uncertainty, and that there were some predictors of missingness, but those correlations weren't overly high. So I haven't got that strong predictors of what those missing values would have been. So the multiple imputation is picking up the fact that there was a lot of uncertainty around these imputed values. So here my multiple imputation is not actually providing any more information, but it's perhaps a more accurate estimate and confidence interval because it's not got the potential for the bias of the missing data. But the main thing here is that the conclusions are the same irrespective, which makes me feel better about my missing data. And then the final step is to report the results from your analysis. So when you're reporting the results, it's very important to describe how much missing data you've got. It's important to describe how you're handling it, in particular, providing the justification for why you're doing it, how you're doing it. If you're using multiple imputation, why are you using multiple imputation? What assumptions are you making? And this is where those causal diagrams come in, because they quite clearly outline what assumptions you're making about the relationships between the missingness and the variables you've got. And then it's also important to report the results from all of the analysis you've done, and think about, how to interpret that in light of the missing data you have. So if you saw differences between your multiple imputation and your complete case analysis, thinking about why the results are different and which one is more believable and why. I know this can be quite a lot of information in the paper, and some of this may well go into a supplementary material, but it's important to have it there to paint the full picture, but also, like I say, point to which analysis you think is the most appropriate. In the case of my case study, I specified MI was going to be done because I had lots of missing data, so that's presented as the primary analysis, and I presented the results from the complete case analysis more in the appendix as a backup. And if you look at that paper in the Journal of Clinical Epi, we put in there some example text of how you might report these things. So actually wording you might use. So that's the whole process. That's everything I really wanted to say. I'll just end with a few concluding remarks. So multiple imputation is extremely powerful in handling missing data, and it makes much weaker and more realistic assumptions than a complete case analysis. And it allows you to include those partially observed participants in your analysis. And it's actually at the stage now where it is quite often requested by journal reviewers because it makes this weaker and more realistic assumption. But you do need to be a little bit careful. You need to make sure that it's justified, and where possible it's pre-planned. It's not you're not playing around with your missing data and getting the answer you want to get. It's important to spend time thinking about developing that imputation model, because that really is the key step. If you want accurate inference, you need to make sure you have a good and appropriate imputation model, and that congeniality comes up all the time in our methodological research as being really important. And then the last point, which I haven't really covered, is you need to think about whether a sensitivity analysis is required. So this is making the assumption that data are missing at random. Like in my example, that quality of life at age 18 wasn't associated with missingness itself, which you can imagine it would be. In that case, you've got data that's missing not at random. So there's analyses you need to do to think about that. And you can do it using multiple imputation, but you need to think about how different the people who don't have complete data are to the ones who do. And that's like I say, that's a whole can of worms and a whole nother talk. But something to keep in mind. So that's everything. I just wanted to acknowledge we have a big missing data group over in Melbourne who have done a lot of research in this area. So that's all those people there. And I want to thank also the group from the Victorian Infant Cohort Studies data set I used. There's a few references for you. The two highlighted in blue are the two I've really run through today. The first one is it runs through all those decisions and some of the justifications or reasoning why you make the decisions and what decisions you have to make. And then there's that framework paper, which is the last part of the talk. And that's everything. So thank you very much for listening. I hope you found it useful and given you a bit of an insight into multiple imputation. Thank you.
Thank you very much, Katherine. That was a comprehensive presentation. I'm going to I see two questions already, and I'm going to ask Mike Kramer to speak first, followed by Sasha.
Thanks, Nandini. Thanks very much, Katherine. That was very well organized and very clear. You didn't say anything. I mean, the variables that you consider imputing the values of. There seems to be no hierarchy between variables that are considered confounders, the primary exposure, or the outcome. I mean, does it matter? I mean, I've read papers, and I myself have done multiple imputations and only imputed confounders and not computed necessarily exposure or outcome. Now, in your case, you knew that there were no missingness for exposure because of the way people were recruited or into your study. But is there any hierarchy, or have people done any empirical research on the degree of bias that can occur in imputing confounders versus exposures versus outcomes?
No, it was a good question. I don't think so. I mean, it's all kind of similar. People do feel a little bit more uncomfortable about imputing outcomes. But I think it still comes down to the same thing, that you're still, if you exclude those people who don't have an outcome or don't have an exposure, you're still potentially biasing your sample. So I think the general feeling is there isn't really a hierarchy, and it doesn't matter. You can impute all of them, and kind of, why wouldn't you? Particularly if you've got strong auxiliary variables.
Has anyone done any empirical research on the degree of bias that occurs when the different types of variables are imputed, or not?
Not as far as I know, no.
Okay. Thank you.
Thanks, Michael.
Thank you. Thank you for that question, Michael. Sasha?
Hi, so my question was similar. So I'm going to sneak in a second question. So I, like Dr. Kramer, I have in my head that it's less okay. In fact, I always thought it was not like kind of verboten to use multiple imputation to fill in the outcome, because that seemed a bit just weird, because the outcome is so important, and how can we just like impute it? So it's interesting, because maybe there are still schools of thought, or maybe maybe the world is not 100% decided on that issue about how okay is it to impute outcomes. But so then I'll withdraw that question and ask you about when you do impute when you're imputing a variable, and you're measuring something multiple times over time. So I think what we talked about was just using almost like a cross-sectional. Is that right? Like your models were kind of looking at one point in time, versus there might be other options if you had a covariate that you're measuring multiple times over time, in which case, for example, if you missed one visit data, you could look at the before and after visit. Hold on just a second. Yeah, so anyway, I don't think you talked about variables that you were collecting over time where you maybe wanted to impute one of the visits. Hope I'm being clear.
Yeah, I think so. I mean, it doesn't actually matter if you have cross-sectional or longitudinal data. It's more about whether you have variables which are associated with those incomplete variables. And the beauty about when you have longitudinal data and you have one visit missing is you're more likely to have good auxiliary variables because you've probably got a similar variable or the same variable measured at the previous or future wave. And that's the other thing I should mention, that you can use future data to predict previous data, because it's all just about information. Because I was going to say, you know, your question, Sasha, link back to the question from Michael about imputing outcomes and feeling uncomfortable about imputing outcomes. You're not actually trying to fill in those missing values. You know, it's about making sure that the inference you get from that analysis is appropriate. So that, I think that kind of makes you feel a little bit better about filling in those unknown outcomes, because that's not the process. It's not really about what values you're filling in. It's about, okay, I'm filling those in, but I'm using that to estimate my treatment effect or my group difference or whatever parameter it is you're estimating. I hope that kind of answers your question, but yeah, I think it's just about which variables are associated with those incomplete variables and can be used to usefully predict what they would have been, which then goes into the analysis.
Thank you. Thank you, Katherine, for your response. Rita Beale has a question.
Thanks very much, and thank you for your very good presentation. My question, again, I guess, relates to the issue of a missing outcome, as the others have pointed out. So I too have seen that, you know, usually there is some hesitation in imputing an outcome. So I'm wondering what your thoughts are on an alternative for dealing with that problem, a missing outcome. And my example is more in a cross-sectional setting. So I'm wondering, because there have been methods developed now for inverse probability weighting, and in particular, if we took this example and sort of treated it more like a selection problem, what I've done in the past is for you know, let's say a larger percentage of data on a missing outcome, I've followed the same procedure very, very closely actually to what you described in looking at sort of the people who have information on the outcome and people who don't. So I would have referred to those people as like participants or non-participants, and then looked at that as a selection issue, and then tried to run a model to look at, to do like a prediction on who was selected and who wasn't based on missingness on the outcome, and then derive from that a predicted probability that could then be used as like an inverse probability of selection weight in the final outcome model. So I just wonder, is that a valid way to deal with that problem as well? It seemed to me like it was, and it seemed to work quite well to try to account for some of those factors that were predictive in my data for the missingness on the outcome.
Yeah, no, I think that's a very sensible suggestion, and we're actually starting to do that a little bit over here too. But like when we've got analyses and the outcome is, you know, along at one of the later time points, we've got bits of missing data in the early part, but then a big chunk of missing data in that outcome. We've been using multiple imputation to impute those missing data, the odd bits of missing data, kind of in the confounders, and then the inverse probability weighting to account for the missing data in the outcome. And we're just in the middle of, one of my PhD students is actually doing a simulation study around that to look at the actual, you know, look at how well it actually performs compared to doing multiple imputation of the outcome. So that will answer a few of these questions. But yeah, Rita, I think that's quite a sensible way of doing it. And like I say, we have been using that over here too.
Oh, great. No, I'm glad to hear that. I wasn't sure how that was going to go over, but I'm glad that it makes sense. Okay, sounds good.
No, it
Thanks.
does. And I think, you know, my example, you could see that the confidence interval was actually a little bit wider with multiple imputation. I think that's because the multiple imputation, you're putting those variables, it's not got that strong a predictor, so it's actually adding uncertainty. And the hope is that using the inverse probability weighting won't actually add as much uncertainty. I mean, we'll find out a bit more when we've done our simulation study, but that, yeah, it may well be a good approach.
Great, thanks so much.
Thank you, Katherine. I just want to take the time to thank you officially. Would we be willing to answer one more question? For 5 minutes. I know we've taken in your family time already.
No, that's okay. That's fine.
All right, just the one will end. So there's a question here from Patricia. Patricia, do you want to speak up? Okay, I'll read her question. If I assume that for lost patients, their missing variables did not change, and I use the last observation carried forward, how does this method compare to multiple imputation in terms of bias?
Last observation carried forward is being shown in quite a lot of scenarios to introduce bias. I mean, it makes a very, very strong assumption, again, unverifiable assumption. So I think last observation carried forward has now been kind of, not shown to be very good. And I think multiple imputation would be better.
Would be certainly preferable to that. Okay.
Yeah.
And but I think I just I'm just wondering though, has there been an empirical study looking to see how many times multiple imputation really made a difference?
No, no. I think it would be a little bit disappointing how often it made a difference actually in reality. I mean, a lot of we show a lot that it does make a difference.
It does.
That's
Okay.
when we kind of look at extreme scenarios in our simulations. When you actually come to do it in our empirical data, it often doesn't make that much difference, but it still makes you feel a lot better about your missing data. You know, if you show that your multiple imputation, your complete case analysis give the same conclusions,
Right.
it makes you feel 10 times better about your missing data. So,
yeah,
but it can. There are a few scenarios where it does make a big difference, but often it doesn't make that big a difference.
And there's software to do it, as you say today.
Yeah, the software is very, very easy to use it and makes it very easy to use. It's just a case of all those decisions you've got to make in the process to make sure you're not actually introducing any more bias.
Right. Okay. Thank you so much, Katherine, and we'll let you go back to your children and your family. Thank you so much.
Sorry for the little pop-up cameo in the middle. It was bound to happen at some point.
Pleasure to see that.